All right, so in this problem, we're going to start with a probability density function, and we are actually going to find the moment generating function of our random variable. And then I thought while we're at it, we might as well use that to find the variance. So let's dive in. We need to remember the formula for the moment generating function. This is a function of t, and it is defined as the expected value of e to the t x, which when we're working with continuous variables like we are, we integrate. Normally we would integrate from minus infinity to infinity, but of course our variable starts at 0, so we're going to go 0 to infinity, and I write down e to the tx times my probability density function. I'm going to put that little 3 out front since it's a constant, so we'll say 3 e to the minus 3x dx, and we should clean this up and write this as 0 to infinity e to the t minus 3 all times x dx. Okay, so we need to take that integral. It would benefit you to remember the indefinite integral of e to the ax dx is e to the ax over a. Of course, we need a not to be 0. I'm going to use that here. I'm viewing this part as my a, as my constant, because I'm integrating with respect to x, and there's my variable x. So this is just a constant. So when I integrate this thing, I'm going to get 3 e to the t minus 3 times x divided by t minus 3. Of course, I really need t not to equal 3 at that point. We'll deal with that more in just a second. And then I'm going to evaluate this from x equals 0 to, a lot of people write x equals infinity. I like to write x goes to infinity, because technically this is an improper integral, which technically means taking the limit of your variable. And I find that a little cleaner. I don't like to write out the limit details when we're preparing for a timed exam where time is precious, but writing x goes to infinity reminds me at least there's a limit involved here. And that's important, because when we come to this, if you let x go to infinity, and let's say this value was, I don't know, 5 or 10, this whole thing is going to blow up to infinity, and we can't even have a conversation. So for this problem to make any sense at all, I need this constant to actually be negative. If I have e to, let's say, minus x, and x goes to infinity, well, that goes to 0, and that's what we want here. So we are actually going to make the assumption, and this is important that you catch this detail because it's not stated in the problem. To be able to have a conversation, I have to have t minus 3 is strictly less than 0, which is equivalent to t being less than 3. And now when that happens, when I take the limit as x goes to infinity, this thing zeroes out, so everything else zeroes out. So I end up with a 0 minus, 3 times 0, but I just got rid of that, 0 minus. And now I simply plug in x equals 0. The numerator becomes e to the 0 times 3, which is just 1 times 3, so I get 3 over t minus 3. You can work with that, or if you want, I'm actually going to pull this negative inside downstairs, and I'm going to get 3 over 3 minus t. And that's it. We just found the moment generating function for x, and it's 3 over 3 minus t, and it's only valid as long as t is less than 3. So that's its domain. Now we can use that to talk about things like expected value and variance. I thought we'd just do variance since it requires both. So let's take the first derivative of this guy, the first derivative with respect to t. And of course, I'm going to get minus 3 minus t squared times minus 1. I'm using the chain rule there. I end up with 3 over 3 minus t squared. And I want to evaluate this thing at 0. So we'll just write down here the first derivative of our moment generating function at 0 is 3 over 3 squared, which is 1/3. And so that is equal to the first moment, which is the mean, the expected value. So expected value here is 1/3, just like that. Now we can use the second moment. Let's compute that. So the second derivative of this guy, working right here, taking derivatives, I'm going to pull that 2 up, if you will. I'm going to get a minus 6, 3 minus t cubed times another negative 1 when you do the chain rule on the inside. And so we end up with 6 over 3 minus t cubed. And then I want to plug in 0, so the second derivative of my moment generating function evaluated at 0 is 6 over 27, which is the same thing as 2 over 9. And that, of course, is the second moment. And so we are almost on our way to the variance. We've basically got it at this point. The variance, of course, is 2/9 minus 1/3 squared. So 2/9 minus 1/9 is, in fact, 1/9. So that's a nice example that illustrates kind of the feel for these moment generating functions, how you can derive them from your PDF, at least in some cases, and how you can use them in the continuous case to work out things like the variance.